Hi everyone. My name is Liza, and today we are going to talk about Apache Spark, more specifically about two things that I believe are most important concepts for writing performance Spark code, lazy evaluations and partitioning. A few words about me. I'm a senior data engineer at Microsoft and also co-founder of Malinina Studio, which is data consultancy agency. I've been in the industry for over 10 years and currently live in Estonia. I also have a 3-year-old daughter, and as you'll see, this fact has deeply influenced the talk and how I think about Spark in general. So let me give you an overview of what we'll cover today. First, we'll do a quick pass on what Apache Spark actually is, just enough context to set the scene. Then we'll talk about lazy evaluations, what they are and why Spark works this way. And after each section, we'll go straight to a demo and see the concepts while they're still fresh. Then we'll have a part on partitioning, how the data is physically organized and why it matters, followed by a demo. And after that, the pitfalls and debugging, caching, checkpointing, and using execution plans to diagnose real problems. Also followed by a demo. And we'll close it with Q&A, but you can also do questions after each section. That's totally great. So, as promised, before we dive in, let's make sure we're on the same page about Spark. Apache Spark is a multi-language engine. It is designed for data engineering, data science, and machine learning. Spark supports Java, Scala, R, Python, and SQL. And the key thing is it runs on single node machines or clusters. And today we'll focus our examples on PySpark, the Python API, but the same can be achieved with other supported languages. So there's three things that make Spark Spark. First, it's a distributed computing engine. Doesn't run on one machine. It splits data across cluster and processes it in parallel. Second, it exposes a data frame API backed by a DAC execution model. So the data frame API is how you write your transformations, and the DAC is how Spark represents and executes them internally. Instead of running your code line by line, it builds a graph of operations and figures out the best way to run them. And we'll explore this deeper today. And the third one, it's designed for high performance. In-memory processing, optimized execution, all of this is by design. Here is how Spark is organized. You have a driver program. This is your code, your notebook, your script, and the driver creates Spark context, which talks to cluster manager. The cluster manager allocates resources on worker nodes. Each worker node runs executors, which have cache for storing data and tasks for doing the actual computation. And this architecture matters because when we say lazy evaluation, it means that the driver is building a plan, but nothing is happening on those worker nodes until you trigger an action. Let's keep this picture in mind. Here's the thing. Imagine you have this perfectly reasonable Spark query. And then you look at your Spark UI and you see that you have 4 shuffles and a 17-minute stage and a lot of output files when you expected just a handful of them. And I've been there quite a few times, and almost always the problem is traced back to one of the two things. Either I didn't understand how lazy evaluation worked, or I didn't understand partitioning correctly. So let's start diving deeper into it from talking about lazy evaluations, and let's start with a story. So as I mentioned, I have a toddler, and there are some challenges with getting them to do things. Here's how a regular conversation can look like if they're occupied with something or not really interested in your requests. You ask them to clean a room, and you know they heard you, but it feels like they're ignoring. You might hear a sound of acknowledgement, but that's about it. A bit later, you ask again, or something else, like putting away the laundry. Same thing happens, nothing is really done. You ask to put away the books, only to hear nothing back. And then you switch to that voice, you say now, and they go like, okay, and only then they actually start doing it, all the things at once that you have requested. The toddler behaved lazy, waiting for the right signal where actions can no longer be delayed. And this laziness is a feature of Spark. Those two types of requests, the gentle voice and the now, have proper names in Spark. The gentle ones are called transformations. A transformation takes a data frame and returns a new data frame. Filter, select, group by, with column, join, all of these are transformations. And transformations are lazy. When you call filter function, Spark doesn't do anything. It just writes down that, noted, I'll need to filter by something later, but there is no data movement. No computation is happening, just like the toddler acknowledging the request. The now voice is called an action. An action produces a non-data frame result. It can be a number, some rows, or writing to the disk, like count, show, collect, or write. These are actions. When you call count, Spark says, OK, now I need to do something. And it takes all the transformations that have queued up, optimizes them, and builds an execution plan, and then runs everything on the cluster. Not all transformations are equal. There are two types of them. There are narrow transformations like filter or select. They work within each partition independently. No data moves between machines. These are quite easy to calculate and quite cheap to calculate. Wide transformations, on the other hand, require data movement. Examples of such are group by, joins, order by. They require data from multiple partitions to end up together, and this is called a shuffle. It's the most expensive thing in Spark. Data gets written to the disk, sent across the network, and then read back. And every shuffle is a stage boundary. Shuffles are where lazy evaluations really shine, because Spark can look at your entire plan and try to minimize how many shuffles actually need to happen. So how does lazy evaluation actually work? All your transformations are queued up until an action is called. Spark builds a plan, it optimizes it, and only then executes. And there are three reasons why Spark is waiting with the execution until the last moment. First of all, it avoids unnecessary work. If you filter early, Spark can push that filter all the way down to the data source and never even read the rows that you don't need. Second, it enables optimization. The Catalyst optimizer could look at your entire chain and simplify it. If you have three separate filters, it will combine them into one. If you don't need all the columns, Spark won't even read them. And the third one, it minimizes data movement. By analyzing the full plan, Spark figures out minimum number of shuffles that are needed. When Spark is building its plan, it creates a DAG, a directed acyclic graph, where directed means that data flows forward, there are no loops, and graph means that operations are connected by data flows. This is Spark's blueprint. It shows all the transformations, shows where stage boundaries happen, and where shuffles are needed. When you open the Spark UI, this is the visual that you see there. And what makes it powerful is that Spark analyzes the DAG before execution. It can rearrange things. This filter should happen before the join, or the two operations can be pipelined. That's where Catalyst Optimizer comes in. Catalyst Optimizer takes your DAG and runs it through three stages. First of all, it's a logical plan. It resolves all column references and checks types. Second one is optimized logical plan. This is where the magic happens. Catalyst applies optimizations like predicate pushdowns, moving filters to the data source so Spark skips entire files. Column pruning, if you only use 3 of 100 columns, Spark won't read the other 97. Filter combining, three filter calls can become one. So this is what it does. And a third one is a physical plan. Catalyst actually generates multiple candidate physical plans and uses a cost model to pick the best one for your specific cluster. And what you see in the Spark UI is the winner of that. Let's have another toddler analogy for this. Imagine a Sunday morning and your child starts firing the requests. They want cereal and milk and juice, but they ask for each one separately, possibly with some pauses in between. An experienced parent knows to wait, just like the Catalyst. collects all the requests, confirms nothing else is needed, and makes one trip to the kitchen. Gets cereal from the pantry and both milk and juice from the fridge at once, without opening it twice. The toddler is eager, and the parent is the optimizer. That's predicate pushdown and operation combining in action. Catalyst is the exhausted but efficient parent who has learned to batch. Here is a proof from a book called Spark in Action. They loaded 2.5 million records and ran 3 experiments. In the first one, they just loaded and collected without anything else, and it took 21 seconds to run. In the second experiment, they loaded, created 3 new columns, and collected the results. It took 34 seconds. More work to do, takes more time, makes sense. In the third experiment, they did the same as in the second one, but they dropped newly created columns before collecting them. You'd expect this to be the slowest since more operations, but it took 25 seconds, faster than just creating the columns. Why? Well, because Catalyst looked at the entire plan, so you're creating the columns just to drop them, and decided I'll just not create them in the first place. It optimized away unnecessary work before a single byte of data moved. This is only possible because Spark waited. If it executed eagerly, step by step, it would have created those columns and then deleted them. Lazy evaluations gave Catalyst the chance to see the bigger picture. And now let's see some of this in action. I will switch to the demo. And before we get into the code itself, a quick word about what you're looking at. This is a Jupyter notebook. If you're used to Databricks or Azure Synapse, the concept is the same. Your document is split into cells, and each cell has code. You run it, and the output appears right below. So I've done the setup here. Spark is started, and the data is on the disk. Let's see how the data looks like. So this is the National Survey of Children's Health, and every row here is one child. Age is calculated or measured in months. We have US states, census regions, also sleep hours, per night, and whether they have regular bedtime, screen time, outdoor play, and a bunch of different scores. And we are working with 5 million records, roughly 7 years of data. I took parts of the real survey and then artificially expanded it to make some Spark more data to work with. And the story we're looking at today is, imagine a 3-year-old who won't sleep, and a parent finds this data set, and they want to know if this is just their child or if there is a broader pattern. So the first question we want to ask is quite straightforward. How many toddlers in the Northeast are not getting enough sleep? So we write it exactly the way we think about it, one step at a time. We filter by region of interest, filter by age, under 3 years, and without adequate sleep. And then we do the aggregation to calculate the average sleep hours and number of such children. Let's run this cell and look at the numbers. So it took only a few milliseconds to run for 5 million rows. That's not because it's a super fast computer. This is just Spark not doing anything yet, because all the filters, all the group bys, these are instructions. And Spark took these instructions, memorized them, and it's now waiting for an action to be called. But nothing happens before that. Now, let's see what happens if we add one more line. We do a count, which is an action on the previous results. And now if we trigger this execution, it takes time for it to generate. And this pauses all the 5 transformations being executed at once across all the rows that we have. So Spark took everything I wrote before, combined it into one single optimized pass, and ran it in one shot. This is what lazy evaluation looks like. You describe the work, and then Spark decides when and how to do it. Now, let's look at another example. Let's say we want a proper report. Total children, average sleep bedtime, regularity, adequate sleep rate, and sleep hours by region. So we are looking at 5 numbers, and the obvious way would be to do it one question at a time. So that's how it's done in this Go. So we have 5 rows with each one doing a calculation. Let me run it, and we can see the timings as well. Oops, it's right here. So it's 5 separate calls, 5 full passes through 5 million rows, because every count and every collect is a trigger, and each one reads from disk. It filters, computes, and then returns. So do we actually need these 5 passes to get the numbers? Not really. There is a way to optimize it. We can combine the requested things together. So here we have the same 5 numbers that are being calculated, but we have put together 4 aggregations into one aggregate call. And that means that we don't need 5 scans and 5 runs anymore. 2 would be enough. And if we run it, so here the identical numbers to the previous one, we can also compare the results. Well, right now it wasn't that much faster. Usually it's about 2 times faster on this machine, but generally that's even not that good of an example because data is stored locally. If you read data from S3 or from other external data storage, reading it every time would cost you much more. But so yeah, on real cluster, it can be a difference between a job that finishes successfully or the one that times out because you're just referencing the data source too many times. This is the column pruning example that's similar to what we saw on slides, where Spark doesn't create the columns it doesn't need. And let's try to reproduce it here. So let's look at the example when we want to create identical 3 new columns and then measure how long it takes for Spark to run it. So to start with, we just do a baseline of the usual data set that we have by just counting it and looking at how long it takes to execute it. Here we create 3 columns and do some aggregations and then collect. So we call an action on it. And on the third example, we create 3 same columns, but then we drop them before counting. Let's run this part of the code. And here are the numbers. Creating columns and using them takes notably longer. Creating the same columns and immediately dropping them is almost, well, it's actually identical in this case to plain count. This is column pruning. So Catalyst reads your entire plan before running anything. And it sees that these columns that were added were then removed before anything uses them. So it never computes them in the first place. We didn't ask Spark specifically to do that. Catalyst just noticed your plan was doing unnecessary work and eliminated it. And we can also have a look at it with the explain command. So these are exactly the same queries, but then we run explain on them to see what Catalyst Optimizer or Catalyst actually plans to do. So the first one is where we call where the columns are required. And we can see that these columns are mentioned in the project. So that's where they're being referenced. In the second one, the columns are never there. The plan is shorter and it just didn't use them at all. Okay. Now, the next example I have was about me writing filters one after another. So we were doing that for all the previous examples where one filter is on one row. So we are doing 4 different filter calls. And I want to know what Spark actually does with it. And we can run same explain command on it. So here it is extended explain, which means that it shows us all the different plans that Spark is doing. So it starts with sparse logical plan. That's what we give them. So it knows 4 different filters. But then when we look at the optimized logical plan, so that's this bit, it already condensed filter into one filter call. So this is our confirmation. It doesn't matter whether you write separate filter calls for readability or chain them on one line. By the time Spark runs, it's the same single pass. The optimizer handled it, so you can write the code that's clearest to you, and Catalyst Optimizer will take care of the rest. We can also have a look at the exchange nodes. So that's where we talked about shuffles in the white transformations. Let's just have another look at the code itself. So we filter by months, and then we do group by and aggregation, and then we do order by. So group by and order by are the functions that are white transformations, and they trigger shuffles. Each exchange mentioned here is a stage boundary, so that's a shuffle, data moving between executors across network. We'll come back to this in the third demo when we talk about explain from another perspective. Okay. That was lazy evaluation and Catalyst in action. We can switch back to slides or take any questions on this part right now, if there are.
There are no questions in the chat.
Okay, then I can proceed for now. So we saw how transformations queue up and optimizer reads the full plan before touching a single byte, and the redundant work disappears. Lazy evaluation determines when and how Spark executes, while partitioning determines what Spark has to work with. Back to toddler examples. Imagine a child who wants to find very specific pieces of Lego. And there are different types of children. Some of them have all the toys dumped into one huge box. How do they find Legos? Well, they dump out everything and dig through it. Cars, dolls, books, just everywhere. A whole 15-minute disaster just to find a few pieces. And now imagine an organized child with labeled bins. Cars in one, Legos in another, dolls in third. If they want Legos, they go to the Lego bin, and that's the job done. That's partitioning. Instead of a giant file, your data is split into organized chunks. If we split them smartly, Spark can skip entire chunks that it doesn't need. Partitioning exists at 2 levels. Let's go through them. There is in-memory partitioning. This is how Spark splits data across executors while it's processing. You can control it with spark.sql.shuffle.partitions, which is defaulted at 200. Each partition maps to one task on one core. So up to 200 tasks can run in parallel, but it's also limited by the number of available cores in your cluster. And on disk, this is how data is physically organized in storage when you write it. You control it by df.write.partition_by and then specify the columns. And it creates a folder structure like year equals 2026 and month equals 5 and so on. The key point is that this enables partition pruning. Spark can skip entire folders that it doesn't need. And the 2 levels connect back to previous part. Partition pruning works hand in hand with predicate pushdown from Catalyst Optimizer. Catalyst pushes your filters down and the folder structure catches it. And Spark never touches the data that it doesn't need. Let's make the impact more concrete and have a look at some numbers. So the timings here are illustrative. They'll vary by cluster, hardware, network, but the data volume reductions are followed directly from maths, so they're real. So imagine we have 1 year of data, about 100 gigabytes in size, without partitioning. If we filter by month, Spark has no way to know where that month's data lives, so it reads everything, all 100 gigabytes every time we ask anything. Now, if we partition by year and month, we have 12 months of data, so Spark creates 12 folders. If we need to query 1 month, Spark goes straight to that folder and reads 1/12 of the data, which is 8 gigabytes. And the folder structure makes it physically impossible to read another 11 months. If we add Parquet with predicate pushdown, it's even better. Parquet stores data in row groups and keeps column level statistics for each one. When Spark applies to your filter, it checks those statistics first. Row groups that can't possibly contain matching rows can get skipped entirely without reading a single value from them. And that's how you can go from 8 GB to half a gigabyte. Most row groups just don't match. The timing will depend on the setup, but data reduction is real. We went from reading 100 GB to half a gigabyte. Lazy evaluation decides when and how to apply those optimizations, but partitioning gave it the structure to act on. And that's the two concepts working together. Let's also cover common mistakes with partitioning. You could have not enough partitions. For example, with 100 cores, only 4 partitions. Only 4 cores are working and cluster is underutilized. It's something that can be fixed with repartition command. It triggers a full shuffle, but gives you even distribution. The next possible issue is having too many partitions. For example, 10K tiny partitions, and the overhead of scheduling tasks and writing tiny files outweighs the parallelism. You can fix it with coalesce. It avoids full shuffle by merging adjacent partitions with minimal data movement. It's cheaper, but can only decrease number of partitions. And you can also end up with skewed partitions. Having one executor processing millions of rows while the rest are sitting idle. It can happen if you partition by country, for example. Sizes of the US and of Estonia are very different, and your code can look fine, but the issue lies in the data distribution itself. There are 2 fixes to that. First one, salting. The idea is simple. You artificially add a random number as a prefix to the key. So US ends up in more partitions than just one. You do a first aggregation pass with salted keys. Now everything is evenly distributed, and then strip the prefix to do a final aggregation to get the real result. There is more code and 2 passes, but no single executor is drowning. And the second fix is AQE. It's adaptive query execution. This is a Spark 3.0 feature, and it changes how Spark plans the queries. Normally, Spark builds the entire execution plan up front before it sees any data. AQE changes that. It looks at the actual data statistics at runtime between stages and adjusts the plan on the fly. For skew specifically, it can detect that one partition is, for example, 10 times larger than the others and automatically split it. It doesn't require any action from your side. Spark just handles it. It became the default nowadays. So if you're on one of the newer versions of Spark, mild skew is often taken care of for you. But for severe skew, salting is still the more reliable fix. And a general rule here is to use repartition before computation, especially heavy computation, and coalesce before writing the data. Let's now go back to demos and have a look at a few other examples that cover these topics. So, okay. At this point, our queries were running reasonably fast, but as we start thinking about adding more years of data or covering more regions, we can pay attention that every query reads all 50 states, even when we only care about Northeast. The data on disk has no concept of geography. Every query reads everything. So let's organize the data. We can write it out in state-shaped folders. That's what this line of code does. We use write mode override just to override the existing data, and we partition by state. We get 50 folders. We can also have a look how it's represented here. Just takes a second to load, and that's it. So we have all our data partitioned and separated by folders, by states. When Spark reads this back, it knows exactly which folder holds which state. Now let's compare what happens if we filter by partition key versus filtering by something else. Let's first start filtering by census region, which is not the partition key. Spark has no way to know which folders contain Northeast records without opening all the 50 files and checking them. Let's run this part of code. It's taking some time to run. Okay, it's taking a bit longer than usually to run. Should get there soon. Here we go. And if we look at the, so it's also at the end showing the explain, so giving us the plan itself. If we look at the plan and we are looking into partition filters, you can see that partition filters are indeed empty. That means that it didn't use any of those. So we lost this benefit of having partition filters. Now let's filter by state, which is our partition key, and look at the explain as well. It was way faster to run. And if we now dig deeper into here, partition filters are indeed being applied. So here, even here, the difference was noticeable, but if the data set is stored in S3, this isn't anymore a minor thing to have. It might be a difference between reading 2 GB and reading 100. But be careful with how you choose your partitions. It should be based on the column that you filter on most frequently. Let's also have a look at reshaping partitions. And before we adjust any numbers of partitions that we have, it's a good idea to check how many cores we actually have. That's what this line of code does. It shows you number of cores currently available. For my machine, it's 6 cores at the moment. And that's our answer for every tuning decision that we'll be making. Here, we're looking at the commands that we just covered. So we have repartition, which is doing a full reshuffle. It's can increase number of partitions. And then coalesce with only partial shuffle is merging adjacent partitions together. Let me run it. We can also see how long it takes for each command to run. As mentioned, repartition triggers full shuffle. So every row gets redistributed across 16 new partitions completely evenly with all 6 cores participating. And it's expensive because data has to move across the network, but afterwards, all partitions are the same size. And this balance matters before heavy computations, where uneven partitions leave some cores doing 10 times more work than others. And coalesce takes the opposite approach. It merges adjacent partitions without triggering a shuffle. It's much faster. The results can be uneven. It's best to use it before writing output when you just want fewer files to be saved. And this one frequently surprises people the most because shuffle partitions defaults to 200. And this number was set in 2013 for large Hadoop clusters with hundreds of cores. And a machine with 6 cores and 50 states, 200 shuffle partitions means that most of them contain almost nothing. And Spark is just scheduling and tracking 200 tasks for no reason. So generally, the rule of thumb is to use 2 to 3 partitions per core. We have 6 cores, so I set partitions to 12. And here we are doing identical transformations. So we are doing group by aggregation and collect, but with different number of partitions. Let's run and see the results. So yeah, having adequate number of partitions means that we process 2.3 times faster, just because of the overhead that the default was adding. So that was partitioning on disk and in memory. Let's now jump back to the slides. Okay. So far, we covered the two promised core concepts. Lazy evaluation, Spark builds a plan, optimizes before executing, and partitioning organizes data so Spark can skip what it doesn't need. Let's now talk about the dark side of Spark's laziness, what can go wrong, and what tools are there to handle these scenarios. I highlighted 3 main pitfalls. Let's take them one at a time. First problem is repeated actions without caching. You want 3 things from the same filter data: account, an aggregated revenue, and the top 5 rows. It looks fine, but each action triggers a complete re-execution of the entire plan. The filter runs 3 times, the data read happens 3 times, and Spark doesn't cache results between actions automatically. To fix that, we can use cache or persist functions. You filter once, all cache, like in here, and every subsequent action reuses the stored result instead of recomputing. Key thing here is that caching keeps the lineage. If a cached partition gets evicted from memory, Spark can recompute it from the original source. But don't cache everything, only what you actually called more than once. And keep in mind that caching also has a cost. Spark needs to perform read and write operations, which also take some time. Second problem is lineage explosion. Think of a toddler, for example, who spent all afternoon stacking blocks one on top of another, all the way up to the ceiling. And then the top one starts wobbling. Same happens with a long pipeline. If you have a 50-stage pipeline and something fails at stage 48, Spark has to recompute all 48 stages because the lineage, the full recipe, goes all the way back to the source, just like all the blocks falling to the floor. On a noisy, overloaded cluster, this can be quite catastrophic. And to fix this issue, we can use checkpointing functions. We can set checkpoint directory and call checkpoint at the midpoint of the pipeline run. Spark saves that state to a reliable storage like HDFS or S3, but it also breaks the lineage. That midpoint is no longer a transformation recipe, it's just a file. If stage 30 fails after that, you restart from the checkpoint, not from the very beginning. And the third problem is debugging confusion. Think of a smoke alarm going off in the hallway, and the toddler is standing right under it, covering ears and staring up in total confusion. But the actual problem is in the kitchen, burnt toast in the toaster. The alarm fires here, but the cause is over there. That's exactly what happens in Spark. You get a stack trace point you can collect, but the actual error about column reference and type mismatch happened 20 transformations earlier. Because Spark waits to execute, all errors surface only at the action call, not where the mistake was made. We can partially fix it with explain. You can call it on any data frame before you trigger an action, and Spark will show exactly what it wants to do. We read output bottom up. So at the bottom, we have a file scan. This is where Spark reads data. We have pushed filters, that's predicate push down. We have partition filters. This is partition pruning. And then moving up, we have partial aggregation right here within each partition, then exchange, that's a shuffle, and then the final aggregation of the results. If you don't see pushed filters or your filter isn't being pushed down, likely it's a UDF or complex expression. If you see the same operation twice, you might be missing a cache. One caveat though, explain helps with planning issues, like wrong column names, missing pushdowns, unexpected shuffles, but it won't catch runtime data errors, like null pointer exceptions or bad casts on actual values. Those still surface at the action, but for performance problems, it's always your first stop to check the explain command. So we have 3 tools, cache, checkpoint, and explain. Let's put cache and checkpoint side by side. If we don't use any cache, we just recompute. It's fine when the operation is cheap or you only need the results once. Caching or persisting stores results in memory or on disk depending on the storage level. It also keeps the lineage. Checkpoint saves to reliable storage and breaks the lineage. It's faster for long pipelines because it eliminates garbage collection pressure and lineage metadata overhead. And oops, here are some real numbers, also from the book Spark in Action. It's same data set, same query. If no cache is being used, it's taking 5 times more time than if cache is being used. And with checkpointing, it's even faster, but then we lose lineage. Generally, a rule of thumb is to cache when you have multiple actions on the same data, and checkpoint when your pipeline is very long or cluster is noisy. Let's also look at the quick cheat sheet of things that I see people getting wrong. Don't run multiple actions on the same data frame without caching. Each action recomputes everything from scratch. It's best to cache before the second action. Don't use collect on very large data sets. It brings everything to the driver to one machine. With big data, you'll get an out-of-memory crash. It's better to use stake for sample or show for preview or aggregation for computing results on the cluster. Don't use UDFs for simple logics. UDFs or user-defined functions are black boxes. Catalyst can't see inside them and can't optimize them, can't push them down. Better use built-in functions whenever possible. Don't ignore explain command. It takes just a few seconds to run and tells exactly what Spark is planning. If it's missing a predicate pushdown or has extra shuffles, it's all there. Don't leave shuffle partitions at default 200. If you have a small data set, 200 partitions of a few kilobytes each is wasteful overhead. And if you have a huge data set on a big cluster, 200 might not be enough. Okay, now let's see a final demo about caching, partition, tuning, and UDFs. All right, here we are. So we keep coming back to the same subset of Northeast toddlers under 3 years of age. Let's calculate how many such children there are and what's their average sleep and what fraction of them have a regular bedtime. These are 3 different questions. And we answer them using the same underlying data set. And every time we run it without caching, Spark treats each one of them as completely fresh job, rewriting the Parquet files and reapplying the filters from scratch 3 times over. So let's run it and see how long it takes with different disk rates. At the moment, it took 2.07 seconds for 3 actions and 3 full scans. Now, if we use cache, so if we cache right after applying filters, this tells Spark that after you compute this filtered subset for the first time, hold it in memory. So the first action, the count reads from disk as usual and stores the result. With the second and third, they don't touch disk at all, and they go straight to memory. Same numbers, but we only paid for the read once. However, we also pay for writing and reading the data, which is why if your data set is not big enough or you read from local files rather than S3 or other external data source, you might actually experience increase in runtime rather than decrease. Let's see how long it takes for me at the moment. And it's likely taking longer exactly because it needs to read and write data. But that's expected on a small machine. When you do that, also don't forget to unpersist. Unpersist clears the memory that belongs to everyone and allows to release resources that you don't need anymore. We have already looked at the explain command a few times. It can be used to read Spark's plan and see what Catalyst has optimized, but now we are going to flip it around a bit and use it as a debugging tool, a way to find the exact things that we just described in the slides. because whether it's a missing predicate pushdown or an extra shuffle or UDF blocking optimization, they'll show up in the plan, and if we know what we're looking for there. So let's imagine a situation that our colleague wanted to label each child as well-rested, borderline, or sleep-deprived based on simple R thresholds, like here. It sounds like a reasonable requirement. They wrote a Python function and decorated it as a UDF, user-defined function. So this decorator right here. And alongside, we have another implementation using Spark's built-in functions when and otherwise. Let's run it. They both give exactly the same output, but when we call explain on them, the plans are very different. So this is the first plan with UDFs, and it shows this batch eval Python. If you ever see that in a plan, that's Spark telling you, I have no idea what's inside this function. It's a black box to Catalyst Optimizer. It can't push it down to the data source, can't combine it with other operations, can't optimize around it at all. The data has to be serialized out to a Python process, run through the function row by row, and then serialized back in. That's exactly the debugging confusion pitfall. It's not just slower, but it's invisible to Optimizer. For the second approach that we took with built-in when function, plan is very different. Well, first of all, you can see that it's shorter because it's optimized, but also we can see here in the projection that it has this case when. That's where it applies the logic that we described. Every condition is visible and the whole thing can be optimized and pushed through the pipeline freely. No serialization, no black boxing. So when a job is slow and you don't know why, this is where I would suggest you to start running explain before you start guessing what is going wrong. If you ever see batch eval Python, that tells you UDF is the bottleneck. If you see more exchange nodes than you expected, likely there is unnecessary shuffles, and maybe it's a good idea to check your partition keys or grouping by logic. If you pushed filters are empty, on a column where you're filtering, it tells you that filter never made it to the data source. So the plan won't fix the problem for you, but it will tell you exactly where to look for the solution. And we have some more time left, so we can cover this demo part as well. This is about salting. It can frequently show up in production, but never can be covered in unit tests, because this is the data skew problem that we talked about. So I artificially pushed 90% of records into California and created a skew data set. And when we run a group by on a state now, Spark has to shuffle all of that data, and California's share ends up in a single partition. So it would be one task handling 4.5 million rows, while other task handles about 10,000. So one executor is doing all the real work, and the rest are sitting idle. And your job runs as long as that one slowest task. So no matter how many cores you have, you are dependent on the slowest task you have running. So it took 0.94 seconds for now to run. And we fixed that with salting. The idea is quite simple. We add a random number. So 0 to 7 for this example, as a prefix to every key before the group by. So we add salting here, and then we do a group by with salted keys. First group by works on the salted keys. It's perfectly balanced across all executors. And then we strip the prefix with regex replace in here, and do a second group by to combine the partial sums into the final result. It's more code and 2 passes instead of 1, but the job is faster because no single executor is drowning. And when I say it's faster on a real big cluster with real big amount of data. On my machine, probably at the moment, it would be slower. Yeah, it's a bit slower than before salting. And this is very expected, and I'll explain why it happens. So salting has an overhead of 2 shuffles instead of 1, extra column operators, and the random call and the regex to replace. And the gain from salting is that it parallelizes hotkey across multiple executors. But on a single machine, even with 6 cores, all those executors are just threads sharing the same CPU and memory. And the thread handling California's 4.5 million rows isn't blocking anyone on a different machine. So everything is local here. We pay for the overhead, but don't get the distributed parallelism benefit. In real clusters, this changes completely. If you have a 200 node cluster, then one task takes 45 minutes to run and every other state takes 2. With salting, you would be increasing the situation dramatically. Okay, these were all the demos I wanted to share today. We can go back to slides and reiterate the main takeaways from the session. 3 things to take away from it. 1, Spark is fundamentally lazy, and that's the point. We don't need to fight it. We just write transformations and trust Catalyst Optimizer to make them better and trigger actions thoughtfully. Second one, partitioning is your data's architecture. It determines what Spark can skip, how well it parallelizes, and how many files you end up with. If we get it right, and you can go from 10-minute full scan to 5-second targeted reads. And third thing is knowing your tooling. Cache when you use data more than once, checkpoint when pipeline is long, and check explain before you start optimizing. It tells you what Spark actually plans to do, not what you think it does. That's the talk. Here I also mentioned the main resources I used. And thank you for your time today. And also thank you to Deborah for being an amazing mentor and supporting me along the way. So happy to take any questions now.